This is our fifth lecture on partial differential equations and how to solve them via Fourier series. Previously, we have seen how to approach the heat equation via Fourier series, and now we're going to do the same thing for the wave equation. Now at this point, we recall that the heat equation is one particularly important partial differential equation because it describes diffusion processes. The wave equation is another prototypical partial differential equation of great importance in physics and engineering. As the name already suggests, it describes wave phenomena. Such wave phenomena appear in acoustics, in quantum physics, in electromagnetism. Of course, traveling waves within water. And so it is right to say that the wave equation is probably one of the most important partial differential equations that we know. The wave equation, generally speaking, models the vibration of an elastic string over time. For example, you might have an elastic rod, you fix its position at both endpoints, and then you induce vibrations. The vibrations, as they propagate throughout this rod, will be described by the wave equation. Let's get a bit more specific. Suppose I've got an interval from 0 to L, which we think of as a parameterization of a horizontal string, and let's say that string vibrates. You've got displacements of the string in the vertical direction. That displacement will change over time, and of course, at every position you've got a different displacement. So it makes sense to model that displacement as a function u that depends on the position x and the time t, uxt. For example, here in the picture, you got one possible such function. Let's say at the endpoints of the interval 0 and L, the string is fixed at position 0, and at some points it's displaced upwards, in which case the function u is positive, and at other positions it's displaced downwards, in which case the function is negative. For example, here at position x, the string is displaced upwards, that is, uxt here is positive. In the model of the wave equation, the string experiences a force in the opposite direction of the vertical displacement. That is, wherever the string is displaced upwards, there's a force pushing it downwards. That is the case at position x. It experiences a force pushing downwards. And on the other hand, wherever the string is pushed downwards, that is, wherever u is negative, it experiences a force pushing it upwards. That is a fundamental setup of the wave equation that we will introduce in the next slide. And let's also recall, often there are external forces. For example, there might be gravity pulling the string down, or any other external force that tries to accelerate the string. Let's put this into a form of a partial differential equation eventually. We focus on the acceleration that the string experiences at any position x and any time t. In the model of the wave equation, the acceleration is the sum of external forces and a term proportional to the curvature. We will visualize the curvature shortly. The acceleration, of course, is a second derivative in time. So at any position x and any time t, we take a look at the second derivative of uxt in time, d squared over d squared t, uxt, and that acceleration term is the sum of two contributions. On the one hand, we got the external force, fxt, and then we've got a force proportional to the curvature, c u prime prime xt, where again u prime prime indicates the second derivative in x of u. That equation is the wave equation. Now, of course, in order to complete the wave equation, we need also initial conditions and boundary conditions. Specifically, we have an initial displacement and initial velocity at time t equals 0. At time t equals 0, we've got ux0 equals u naught x, where u naught x denotes the initial displacement, that is the initial position. And furthermore, we have d over dt ux0 equal v naught x, which indicates the initial condition on the velocity. v naught is the initial velocity at position x. And what's more, apart from the initial conditions, we also have got boundary conditions. We assume that we can control the displacement at the boundaries u0t equals g0t for any positive time t, and ult equals glt for any positive time t. That is, we fully control the position of the string at the boundary. That may actually change over time, but in practice, we will assume that we have got fixed positions over time. In fact, more specifically, we will assume that the boundary positions are just 0. Let's have another look at this curvature force, c times u prime prime. Here is a prototypical situation. Let's say the string has got a displacement upwards. It will, generally speaking, have a form similar to the one depicted here. As you read the graph from left to right, first the displacement goes up and then down. The first derivative of u prime, first goes up and then down. First it is positive and then glides into the negative. As we go uphill, it is positive, and as we go downhill, it is negative. So in particular, u prime prime will be less than 0. In the situation depicted here, however, we also have a force due to the curvature pushing the string downwards. And that force will be proportional to the second derivative of u. Now let's have a look at an example. This is a classical example for the wave equation over a finite interval. We've got fixed boundary values at the endpoints of the interval. We've just fixed the function to 0. And here we start with some non-zero function, basically just a sine curve. In this example, the initial velocity is 0, there's no external force, but the initial function, the initial value u0, is non-zero. In fact, it's just some very simple sine curve. And as we start the evolution, the wave equation behaves exactly as you would expect. We see the movement of an oscillating string. The acceleration of the graph is fastest where the second derivative is further away from 0. For example, whenever the oscillation reaches its maximum, the acceleration is fastest, and then as the string moves due to the acceleration towards 0, well, it overshoots, because at that point the acceleration has generated enough velocity, so the string overshoots. It crosses 0 but does not stabilize at 0, and so the oscillation continues. In contrast to the heat equation, where in many cases we observe an asymptotic steady-state solution as time goes to infinity, in the wave equation we do not observe any stabilization. The oscillation just keeps on and on for all times. What's more, in a mathematical precise sense, the energy contained in that system stays constant over time. As with any other differential equation, there are two basic questions associated also with the wave equation. Namely, does a solution exist, and is a solution unique? And as before, we address the question of uniqueness first, because showing uniqueness in fact is easier and pretty much standard. So let us suppose we got two solutions to the wave equation, u1 and u2. To show that the wave equation has got a unique solution, we need to show that u1 and u2 are the same. And as before, we will do that by taking a look at the difference between these two solutions. So let's define v as the difference of u1 and u2. It is easily seen that v itself satisfies a homogeneous wave equation. Specifically, the second time derivative of v at xt minus c times the second spatial derivative of v equals 0 for all values of x between 0 and L and for all positive times t. What's more, for t equals 0, we see that vx0 is 0 and the first time derivative of v at x0 is equal to 0 for all x in the interval from 0 to t. For all positive times t, we have that v0t equals 0 and vlt equals 0. That is, the function v satisfies the wave equation with a homogeneous external force. It satisfies homogeneous initial values and homogeneous boundary conditions. We want to show that v equals 0. That will show uniqueness. And to do so, we take a look at the energy of the system. That is a new concept. But we've seen something similar before in the discussion of second-order ordinary differential equations. So let us take a look at the energy functional, E of t equal 1/2 of the integral from 0 to L of the square of the first time derivative of v xt plus c times the square of the first x derivative of v at xt dx. That is the energy of the system. Let's take a look how the energy develops over time. To see how the energy develops over time, let's compute the time derivative of the energy. So, d over dt et equals 1/2 of d over dt of the energy, the integral from 0 to L of the square of d over dt vxt plus c times the square of the first x derivative of v xt dx. The integral is in the x variable, in the position variable, and the derivative is in the time variable. So we can just pull in the derivative into the integral and compute the time derivatives of those two squares. What we get then is the integral from 0 to L of the second time derivative of v xt multiplied with the first time derivative of v xt plus c times the derivative in space and then in time of v xt multiplied with the first x derivative of v xt dx. So we integrate two products. And before we proceed, we will take care of the last term, the last product. Namely, we want to untangle the two derivatives in space and time. And that is done via integration by parts. In the last product, the integral from 0 to L of time derivative and space derivative of vxt multiplied with space derivative of vxt dx. What we do is we roll over the first x derivative in the left factor onto the other factor. So integration by parts tells us that the left integral equals the x derivative of v times the time derivative of v evaluated at x equals 0 and x equal L minus the integral from 0 to L of the second space derivative of v times the first time derivative of v dx. So what do we do with this term at the boundary values? Well, we notice that v is actually constant at the boundary points. So in particular, the time derivatives there are 0, and we conclude that this middle term for x equals 0 and x equal L is just 0. So we are only left with the last integral on the right hand side. Let's plug this in. The first time derivative of the energy Et equals the integral from 0 to L of the second time derivative of v times the first time derivative of v minus c times the second space derivative of v times, again, the first time derivative of v dx. And now we can just reorder this. So the time derivative of the energy equals the integral from 0 to L, and now we factor out the first time derivative of v. We have the product of the second time derivative of v minus c times the second space derivative of v, and that difference is multiplied with the first time derivative of v dx. Now the important observation is that v, of course, solves the wave equation with homogeneous force term, and so the left factor in this last integral is actually 0. In particular, the energy has time derivative 0, that is, it is constant. So the energy remains constant in time. Since the energy is constant in time, it always retains the same value it already has at, for example, t equals 0. But for t equals 0, we can explicitly compute the energy. Namely, E of 0 equals 1/2 of the integral from 0 to L of the square of the first time derivative of v x0 plus c times the square of the first x derivative of v x0 dx. But on the one hand, we know from the initial data that the time derivative at t equals 0 is equal 0, that the time derivative at t equals 0 vanishes, and since the initial data were assumed to be constant, we also know that the x derivative at t equals 0 just vanishes. So in particular, the energy at t equals 0 just vanishes as well. The initial energy is 0, so the energy is always 0 for all times. Now, if you take a look at the definition of the energy, it can only be 0 if at all times the time and space derivatives of v are 0. And that just means that v is constant in space and time. And so, finally, since we recall that v is 0 at the very beginning, we conclude that v is 0 everywhere at all times. In particular, u1 and u2 are always the same, which had to be shown. That shows the uniqueness of the solution. And now let's address the existence of the solution. Showing the existence of a solution will again be done via a Fourier series. The basic assumption is that we can represent the data of the problem in terms of Fourier series. So we assume that the fourth term can be represented by a Fourier series at all times. And of course, the coefficients in that Fourier series will again be time dependent. So let's introduce the notation. f(xt) equals a of 0t plus the sum starting at n equal 1 going up to infinity of a of n of t times the cosine of 2 pi n x over L plus b of n of t times sine of 2 pi n x over L. Again, the coefficients depend on time. We also assume that the initial data can be represented by a Fourier series, in which case, of course, the coefficients will not be time dependent. They will just be ordinary coefficients. So we assume that u0 of x equals a0 naught plus the infinite sum starting at n equal 1 up to infinity of a0n cosine 2 pi n x over L plus b0n times sine 2 pi n x over L. And we assume that v naught x equals av0 plus, again, the infinite sum from n equal 1 up to infinity of avn times cosine 2 pi n x over L plus bvn sine of 2 pi n x over L. Since we assume that the data of the problem can be represented as Fourier series, we also do the same for the proposed solution. So let's assume that the solution can be represented by a Fourier series. And since the solution, of course, is a function both in space and time, the coefficients in the Fourier series will also be time dependent. So we assume that uxt equals a0 of t plus the infinite sum starting at n equal 1 going up to infinity of an of t times cosine 2 pi n x over L plus bn of t times sine 2 pi n x over L. We will show the existence of a solution to the wave equation by explicitly constructing a solution from the data of the problem. And that boils down to finding the Fourier coefficients of the solution. Before we proceed, we do one important simplification of all this. Namely, as already discussed in the context of the heat equation, we will only use a Fourier sine series. That is, the constant term and the cosine terms are all assumed to be 0. That is, for all n greater equals 0, we have got that an equals a0n equals abn equals afn equals 0. With that set up, let's get to work. Since we deal with the partial differential equation, it makes sense to take a look at the derivatives of the solution and how those can also be expressed in terms of Fourier series. Let's first have a look at the time derivatives of u. To compute the first time derivative of u, we just take the time derivatives of the coefficients. So, the first time derivative of uxt equals the infinite sum of b prime n of t times sine 2 pi n x over L, and the second time derivative of uxt equals the infinite sum of b prime prime n of t times sine of 2 pi n x over L. And similar as in the discussion of the heat equation, the first x derivative of u equals the infinite sum of bn of t times 2 pi n over L times cosine 2 pi n x over L. And the second derivative of u and x equals the infinite sum of bn of t times negative 4 pi square n square over L square times sine of 2 pi n x over L. What we need is only the second derivatives. Let's see how this works out in the context of the wave equation. We integrate both sides of the wave equation with the Fourier sine modes in order to extract a relationship between the coefficients. So for some index n, let's take a look at the integral from 0 to L of the second time derivative of u xt times sine 2 pi n x over L dx minus c times the integral from 0 to L of the second x derivative of u xt times sine 2 pi n x over L dx, and we know that equals the integral from 0 to L of fxt times sine 2 pi n x over L dx. Now on the right hand side, we know that integral just equals the nth Fourier sine coefficient of f at time t up to some factor 2 over L, and the two integrals on the left hand side, they just extract the Fourier coefficients of the second time derivative and the second space derivative of u. Again, up to a factor 2 over L. And so we can extract a second order differential equation satisfied by the nth Fourier coefficient of the solution. We have bn prime prime of t minus c times bn of t times negative 4 pi square n square over L square, and that equals bfn of t. That is a second order differential equation. The unknown function here is bn, which is a time-dependent function. We see there is a second derivative of bn, there are some coefficients, and on the right-hand side, the data of the problem is a time-dependent term, bfn, which we assume is known because that's part of the data. So it remains to solve the second-order differential equation. And similarly, we also extract the initial conditions for the second-order differential problem just by taking a look at the initial conditions of the wave equation. So we see that the integral from 0 to L of ux0 times sine of 2 pi n x over L dx equals the integral from 0 to L of u0 of x times sine 2 pi n x over L dx. And that's clear because u satisfies the initial conditions. Similarly, we also have that the integral from 0 to L of the time derivative of ux0 times sine 2 pi n x over L dx. That equals the integral from 0 to L of v0 x times sine 2 pi n x over L dx. Those two equations extract the initial data of the ordinary differential equation. In the first equation, we can extract that bn of 0 equals b0 n, and in the second equation, we extract that b prime n of 0 equals bvn. Again, we use that integration against the nth Fourier sine mode extracts the nth Fourier sine coefficient. We do that on all sides of the equations. To summarize, the second order ordinary differential equation, together with the initial values, has the following form: b prime prime n of t plus c 4 pi square n square over l square times bn of t equals b of n of t, with initial conditions bn 0 equals b naught n and bn prime of 0 equals bvn. So we have this second order initial value problem, and in order to solve it, we can apply any solution technique for such initial value problems. For example, the Laplace transform. So let's get on with the second order ordinary differential equation. Let's take a look at b and prime prime of t plus c 4 pi square n square over l square times bn of t equal bfn of t. Now, to simplify the discussion, that coefficient c times 4 pi square n square over l square, we will just write capital K for that one. Just to simplify the following formulas a little bit. The idea to solve this ordinary differential equation is to apply the Laplace transform to the entire ordinary differential equation. And again, we introduce some notation. Let us write capital B of z for the Laplace transform of Bn at z, and let us write f of z for the Laplace transform of Bfn of z. With that notation, if we now apply the Laplace transform to the second order ODE, we get the following identity: z square times bz minus z bn 0 minus bn prime 0 plus k bz equal f of z. Here we have just used linearity of the Laplace transform and the formula for taking the Laplace transform of derivatives. The plan is again to isolate bz. With some simple manipulation, we see that k plus z squared times bz equals f of z plus z bn 0 plus bn prime 0. We just regroup this equation. Dividing by k plus z squared, we see that bz equals f of z plus z bn 0 plus bn prime 0, all divided by k plus z squared. Now, to get the coefficient bn, we would like to apply the inverse Laplace transform to both sides of the equation. However, with some other manipulation, we can also just look up Laplace transform from a table, and that is what we're going to do. So that big fraction can be decomposed into the sum of three simpler fractions. We have f of z divided by k plus z squared plus bn 0 times z divided by k plus z squared plus b prime n of 0 divided by k plus z squared. We treat each of those terms separately. First, we have a look at the term bn prime of 0 divided by k plus z squared. Now, the numerator is just a constant, and so we just need to look up the inverse Laplace transform of 1 over k plus z squared. So in total, that first fraction has the inverse Laplace transform bn prime 0 times sine of square root k times t divided by square root k. Next, we have a look at the term bn 0 times z divided by k plus z squared. The difference now is that the numerator also got the factor z. bn of 0 is just some constant term that we can factor out, and looking up the inverse Laplace transform from a table shows that the second fraction is the Laplace transform of the term Bn0 times cosine square root k times t. Lastly, we have a look at f of z divided by k plus z squared. That term, of course, is a bit more complicated, but we see it is a product of two Laplace transforms. It is a product of 1 over k plus z squared times f of z. For each of those two factors, we already know the inverse Laplace transform. And now we can use the convolution theorem of the Laplace transformation. And that tells us that the third fraction has got the inverse Laplace transform given as follows. The integral from 0 to t of sine square root k times s divided by square root k times bfn of t minus s ds. Okay, so we have found the inverse Laplace transforms of all these terms, and we can plug in the initial data for bn0 and bn prime 0, and that leads in the end to the following solution formula. The solution is bn of t equal bn0 times cosine square root k t plus bn prime 0 sine square root k times t divided by square root k plus the integral from 0 to t of sine square root ks divided by square root k times bfn t minus s ds. From the initial data, we can slightly simplify this to get a closed formula that equals b0n cosine square root k times t plus bvn sine square root k times t divided by square root k plus the integral from 0 to t sine square root ks divided by square root k times bfn t minus s ds. That is the solution formula. An interesting special case is when the fourth term f does not depend on time. In that case, the coefficients in the Fourier series of f are also time independent. The only change applies to the last integral. If we assume that the coefficients of f are constant in time, we can just factor out bfn in the last integral. We can also factor out 1 over square root k. So the last term becomes bfn 0 divided by square root k times the integral from 0 to t of sine square root ks ds. We can explicitly compute the last integral, and therefore we get the following form for the last term. The constant bfn divided by k multiplied with 1 minus cosine square root k of t. In particular, what we can tell from the last formula is if the fourth term f does not depend on time, then the solution will be periodic. It's just a superposition of cosine and sine functions. In this example, we have a look how solving the wave equation via a Fourier series looks like. We use the Fourier series to approx initial values that are piecewise constant and alternate between 0 and 1. We've seen such initial values before, and we've seen that we can approximate them using a Fourier series. However, we only take a few terms from the Fourier series, up to 25. So we still see the wiggles of the sine function of the Fourier sine modes. And as we let the evolution start, we see that the wave equation produces these patterns of traveling waves. The pattern just keeps going on forever. We finished this lecture with a few remarks on the differences between the heat equation and the wave equation. As you might expect, they describe two very different phenomena, diffusion and wave propagation. And so there are some properties of the solutions that we can distinguish at this point. For example, we have seen that the heat equation, if the data are constant, converges to a steady-state solution. That is a solution that does not depend on time anymore. It stays constant. By contrast, the wave equation, generally speaking, does not converge to a stable limit. Furthermore, in the heat equation, information is lost. For example, the influence of the initial heat distribution just vanishes over time. And in particular, the heat equation is not time reversible. If you let the heat evolution run backwards, you don't get any physically meaningful process. For example, it's not physically meaningful that heat clumps together. By contrast, the wave equation is time reversible. If you let the solution of the wave equation run backwards, so to speak, it looks just as fine. And in particular, no information is lost over time. And we've also seen hints of the fact that the wave equation is energy conserving, unless there's an external force term. In upcoming lectures, we will also have a look at speed of propagation. In the wave equation, information travels with a finite speed, whereas in the heat equation, you've got an infinite speed of propagation. For example, in the wave equation, common phenomena are traveling waves that move with a certain speed that depends on the coefficients, whereas in the heat equation, then as soon as you let the heat evolution run, heat diffuses out over the entire interval, just immediately. So up to now, we have discussed partial differential equations over a finite interval, and we've discussed it in terms of Fourier series. In the upcoming lectures, we will take a look at partial differential equations over infinite intervals. In that case, we use not the Fourier series, but the Fourier transform. More about that in the next lecture.